Hello everyone, this is lecture 2 of week 9. Recall that in the last lecture we learnt certain characteristics of linear programming problem, right. So, we learnt that the constraint set of a linear programming problem will always be an n dimensional polytope, right, and we also learnt that one of the solutions of linear programming problems will always be a vertex of the feasible polytope, right. All right. So, given that these are some characteristics of a linear programming problem, Danzig actually proposes a simplex method where we are actually characterizing the vertices of a linear programming problem mathematically. Okay. And how are we doing it? The first step is to convert the given problem min C transpose x subject to Ax less than or equal to b, a bar x less than or equal to b bar, to a problem where you are minimizing C transpose x subject to a dash x equal to b dash x greater than or equal to 0, where a dash is an m cross n matrix with rank of a equal to m. Okay. So, fine. How do we do it? I will actually illustrate that with an example. Okay. So, then we will understand how to do this generally. Okay. We will of course take our usual example, the triangle example, where you have minus x1 plus x2 less than or equal to 0, x1 plus x2 minus 1 less than or equal to 0, and minus x2 less than or equal to 0, right. So, the constraints that we have is minus x1 plus x2 less than or equal to 0, x1 plus x2 minus 1 less than or equal to 0, and x2 greater than or equal to 0, we will write it that way. Okay. Now, I do not like inequality constraints because I want equality constraints here, right. So, how can I convert this into an equality constraint? Okay. Very simple. I will write it as following. I will write this as minus x1 plus x2 plus x3 less than or equal to 0 and x3 greater than or equal to 0. So, if I convert equal to 0, yeah. So, this is minus x1 plus x2 plus x3 equal to 0, where x3 is greater than or equal to 0, right. I am saying that this constraint and these set of constraints are actually equivalent. Why is that? Because, so suppose you have an x1 x2 in such a way that it is less than or equal to 0, what it means is that you can add a positive number and make it 0, right. It is as simple as that, isn't it. So, that is what we are actually doing here, right. So, we are adding a variable x3 which is actually non negative, right. So, since minus x1 plus x2 is non positive, right. So, if you add the negative of this, so say x1 minus x2, right, to this, it becomes 0, isn't it. So, adding this slack variable x3 such that it is non negative, right, helps us to convert an inequality constraint to an equality constraint and a non negativity constraint. Okay. Note that both of these are equivalent. Okay. So, I can write it this way, which are, I mean, this constraint and these pair of constraints are actually equivalent. I am going to do the same thing here. So, this x3 is actually called as a slack variable. Okay. I mean, in some of the literature people call it dummy variable. Okay. So, but in standard optimization literature it is called slack variable. So, I use that term. Okay. And similarly here, this will be equivalent to x1 plus x2 plus x4 minus 1 equal to 0 or equal to 1, both are the same. Okay. So, if I bring this here, so I am just going to add a slack variable here, and of course x4 has to be non negative. It is the same technique. So, if x1 plus x2 is less than or equal to 1, you add a non negative slack variable and you can make it equal to 1, right. So, both of these constraints are equivalent, and just that x4 is now a slack variable. All right. So, now we have written these set of constraints whatever we have here, right, minus x1 plus x2 less than or equal to 0, x1 plus x2 minus 1 less than or equal to 0, x2 greater than or equal to 0, as you have equality constraints, 2 equality constraints and 3 inequality constraints x2, x3, x4 greater than or equal to 0. We are still not done because we do not have x1 greater than or equal to 0, right. So, x1 here is unconstrained. So, if I just write down the converted form of this, I will only have minus x1 plus x2 plus x3 equal to 0 and x1 plus x2 plus x4 equal to 1 and x2, x3, x4 greater than or equal to 0. So, it is not exactly this because you do not have x1 greater than or equal to 0, right. So, that is some possibility. You might have variables which are unconstrained, not having such nice constraints as this this form, right. So, I mean that is you do not have the non-negativity constraints. Okay. So, what do you do if it is unconstrained, if it is not constrained as with non-negativity, right. That is simple as well, right. So, you just create 2 variables instead of the one unconstrained variable. Okay. So, that is I am going to create, I am going to write x1 as x1 plus minus x1 minus. Okay. So, what does this mean? It means x1 plus is actually max of 0 comma x1, right. So, if x1 is non-negative, then x1 plus is just x1. Okay. I am sorry, yeah. And what is x1 minus? X1 minus is 0 if it is positive, if x1 is positive, and minus x1 if x1 is negative. Okay. So, this is actually max of 0 comma minus x1. Okay. So, if x1 is positive, this is 0, if x1 is negative, then minus x1 is positive. So, max of 0 comma minus x1 will be minus x1 itself. Okay. So, that is if for example x1 is 4, then x1 plus is 4 and x1 minus is 0. If x1 is minus 4, then x1 plus is 0 and x1 minus is 4. Okay. Because of that, you can see that both x1 plus and x1 minus are non-negative. Okay. So, now I will write these set of constraints as, yeah, wherever you have x1 you have to replace it with x1 plus and x1 plus minus x1 minus. So, because of which the first constraint becomes minus x1 plus x1 minus plus x2 plus x3 equal to 0, and the second one becomes x1 plus minus x1 minus plus x2 plus x4 equal to 1, and here you have 5 variables now, x1 plus, x1 minus, x2, x3 and x4, right, and all of them are non-negative. So, you have x1 plus, x1 minus, x2, x3, x4, all of them are non-negative. Okay. So, I had these set of constraints where, yeah, it was of the form Ax less than or equal to b, you had even no equality constraints either, right. I have now converted it as of the form a dash x equal to b. So, you only have equality constraints and all the non-negative constraints are non-negativity constraints of the variables, and every variable is constrained to be non-negative. Okay. So, all that has been accomplished. Okay. But I still have to check if the A dash matrix that you have is having a rank equal to m, right. So, let us do that. So, you have the A dash matrix that you have here is minus 1, 1, 1, 1 and 0. Here you have 1, minus 1, 1, 0 and 1. Okay. So, it is a 2 cross 5 matrix and I want the rank to be 2. Of course, the rank of this matrix is 2 because, yeah, so one is not the multiple of the other, right. So, one row is not the multiple of the other row, right. So, it is very clear that A dash is actually of rank 2. Okay. So, rank of A dash equal to 2. Okay. So, we have actually converted, at least in this example, right. So, we started with a constraint set of this form Ax less than or equal to b, and we have converted it into a form where it is a dash x equal to b dash and x is non negative. Okay. So, good, I mean, so yeah, at least for this example we were able to do it, but how would you do it for a general linear programming problem? Do you have a nice way of accomplishing this? It turns out that we can. Okay. So, I mean, we just have to follow the following steps. Okay. So, I will write that down now. Okay. So, the first step, so you can say steps to convert an LP into a standard form. Okay. So, this form whatever we have here, right, this one. So, this is actually called as the standard form. Okay. So, the first thing that you have to take care is, so I mean, since you might be given a more general problem than what we have given here, right. So, you could have a maximization here, you might have some greater than or equal to constraints, right. So, I mean, those need to be checked in the first place, right. So, so first convert maximization to minimization by, I mean, adding a negative if at all it is there. Okay. Maximization into minimization. Convert greater than or equal to into less than or equal to, right. So, if yeah, you have a constraint like x1 plus x2 greater than or equal to 0, write it as minus x1 minus x2 less than or equal to 0. Okay. So, that is the first step you have to do anyway. Okay. The second step is, if you have a constraint ai transpose x okay, less than or equal to bi, so that should become ai transpose x plus some slack variable, call it xs, I mean, yeah, it could be anything else, I am just giving an illustration, right, equal to bi xi greater than or xs greater than or equal to 0. Okay. So, yeah, I should say this. If you have this, then make it this. So, whenever you have an inequality constraint that is less than or equal to, since all are less than or equal to, right. So, you can make any ai transpose x less than or equal to bi as ai transpose x plus x is equal to bi, x is greater than or equal to 0. So, when you do this, yeah, you are converting it into standard form. Okay. Then, when a variable is unconstrained, okay, maybe I will write as xi, xi is unconstrained, then convert it as xi equal to xi plus minus xi minus. Okay. So, and so when you do this, you can also include xi plus non negative and xi minus as non negative. Okay. So, in each equation xi should become xi plus and xi minus. Okay. And you should add the constraints xi plus non negative and xi minus non negative. Okay. So, when you do all of these steps, you would have actually converted into this particular form where you have a dash x equal to b dash and x non negative. Okay. But we are still not done, because we do not know if rank of a is equal to m. So, yeah, in this case it turned out to be easy, I mean, yeah, it was I mean, rank of a equal to m, we just got it as such, right, but in general we may not get it. Okay. So, if that is the case, suppose you have an m cross n matrix, but the rank is less than m, say m minus 2 for example. Okay. Then what do you do? Okay. So, it is simple, just cancel out the rows, I mean, or rather, I mean, you choose m minus 2 rows out of m in such a way that those m minus 2 are linearly independent. Okay. So, let us say the rank of A is equal to rho, which is less than m. Okay. So, if the resultant constraint A dash x equal to B dash x greater than or equal to 0 is such that rank of A dash equal to rho less than m, okay, then choose row linearly independent rows from A dash and let that be the resultant set of constraints. Okay. So, maybe I will just give an example of how we need to do this. Okay. Suppose you have A dash is this 1 2 3 2 4 6 and 2 4 5, okay, x1 x2 x3 equals say some 4 8 and 2. Okay. I am just writing whatever comes to my hand. Okay. So, so this matrix is 3 cross 3. So, you need to have the rank to be 3, okay, but I mean basic linear algebra should tell you that the first and second rows are dependent, right. So, twice the first row is the second row, right. So, that means they are actually dependent, right. So, you will have to, so the rank is actually 2 because the third one is not dependent on the first or the second. Okay. So, you cannot choose 1 and 2 because if you choose 1 and 2 then they are not linearly independent rows, okay, but you can choose 1 and 3, they are linearly independent, and you can choose 2 and 3 as well, they are also linearly independent. Okay. So, you can choose any of the 2 linearly independent rows, okay, and the resultant set of constraints will either be 1 2 3 2 4 5 x1 x2 equals 4 2 or 2 4 6 2 4 5 x1 2 8 2. Okay. So, one of them will be the resultant set of constraints. Okay. So, when you do all of these steps, okay, you would have actually converted any given linear programming problem to its standard form. Okay. So, that is very important, fine, but I mean okay, this is actually the first step in finding out the vertices. We have still not found the vertices, please understand that. Okay. So, we have just converted the given linear programming into its standard form. Okay. So, now what we have is the standard form. Okay. Standard form of LP, okay, which is min C transpose x subject to, I will write it as Ax equal to B. A dash was written because I mean I wanted to differentiate it from A and A bar. Okay. But otherwise you can use any notation with so A is an m cross n matrix and rank of A equal to m. Okay. All right. So, now note that you have an m cross n matrix and the rank is m. We know that the rank is less than the number of rows as well as the number of columns, right. So, if it is equal to m, then it is certainly less than or equal to n, is not it. So, what this means is that the number of rows is less than or equal to the number of columns, only then this can happen. If it is greater, certainly the rank of A is not m. So, So, keep that in mind. The A is actually like a rectangular matrix like this, right, because the number of rows is less and the number of columns could be higher. Okay. So, now you have n columns, right. In these n columns you can actually choose m linearly independent columns, is not it. I mean, that is again basic linear algebra. So, if the rank of A is equal to m, that means you can choose m linearly independent rows and m linearly independent columns from the given matrix, right. So, let us actually choose m linearly independent columns from A, okay, since the rank is actually equal to m, okay, and let us call that, I mean, those set of columns as B, okay. The remaining set of columns will be called n, okay. In other words, so note that A has A1 is one column, A2 is another column, A3 is another column, dot 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 An. So, you have n columns and m rows. I mean, each A1 is an m length vector, a vector of length m. A2 similarly is an m length vector, dot 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 An is an m length vector, okay. So, each of this is a vector. Now, yeah, let us say that A1, A2, dot 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 Am are linearly independent. I mean, that is just without loss of generality, otherwise you can, I mean, exchange the columns in such a way that the first m columns are linearly independent, right. So, let A1 dot 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 Am be linearly independent, okay. So, I can now write this as, yeah, A1 dot 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 Am plus 1 dot 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 An, right. Just to differentiate what is going on. I am going to call this matrix as B. B is an m cross m matrix and n is n minus m cross m matrix, okay. So, now and similarly for x I will write the variables corresponding to A1 to Am as the basic variables, which is, yeah, in this case x1 to xm, and the remaining variables are called non basic variables. So, I will write them as xb and xn, right. So, yeah, now Ax, so Ax equal to B becomes Bxb plus Nxn equal to B, right. Note that Xb is an m cross m matrix with rank equal to m, which means the matrix B is capital B is actually invertible. Please keep that in mind, okay, because it is an m cross m matrix with rank m, okay. So, that is invertible, okay. Now, suppose I choose xn to be 0, okay. So, this is actually like, so yeah, I mean, yeah, I am calling this as basic variables and non basic variables, okay. Xb is basic variables and xn is non basic. So, that is the reason we call that with the letters B and n, okay. B is basic and n is non basic, okay. So, yeah, so in simplex method we call them as basic and non basic variables, okay. So, if you have learnt, let us say, Gauss-Jordan method, okay, you would have possibly used the term free variables, okay. So, non basic variables are actually free variables, you can choose any values, that is basically it, okay. So, suppose I choose the free variables, that is the non basic variables, all as 0, okay. So, if xn equal to 0, that is yeah, so these n minus m variables becomes 0, okay, then xb is actually B inverse B, capital B inverse small b. Okay. So, one of the solutions of A x equal to b, okay, is x b x n equals b inverse b comma 0. Okay. Now, why is this interesting? Yeah, of course, this is one of the solutions. There are many such solutions, but why is this solution so interesting? It is because any solution of the form b inverse b comma 0 is a vertex of the set of equations A x equal to b. Okay. Not just that, the converse is also true, that is any x of the form b inverse b comma 0 is a vertex of the set of constraints A x equal to b. Okay. So, yeah, I am not going to prove this, but I mean to see why that is the case, you can actually see that when you have A x equal to b, x greater than or equal, yeah, I should have said with x greater than or equal to 0, yeah, otherwise it is not correct. Okay. So, yeah, so if you maybe I will write that down and correct my statement. Okay. So, consider A x equal to b, x greater than or equal to 0. Okay. Then x b x n equal to b inverse b comma 0 is a vertex. So, maybe call this f, okay, f for feasible set. Okay. So, let us say the feasible set is characterized by maybe I will write x such that, okay, f equal to x such that A x equal to b, x greater than or equal to 0, then this b inverse b is a vertex of f if b inverse b is greater than or equal to 0. Of course, that is not a given, I mean b inverse b can have some components where it is less than 0, okay, but if it turns out that b inverse b is greater than or equal to 0, then this is certainly a vertex of f. Conversely, okay, any vertex of f has a b and n such that x b comma x n equal to b inverse b comma 0 and with b inverse b non negative. Okay. So, yeah, these are actually important, and that is the reason we actually converted I mean any given linear programming problem to its standard form, okay, so that we can easily locate the vertices of the linear programming problem. Okay. So, yeah, we will continue in the next class, and we will see a little more about the vertices before actually explaining the algorithm in detail. Thank you.